So previously we learned about high resolution NMR spectroscopy, or specifically when we're talking about a high resolution NMR spectrum, okay, we're looking for a few different things. Right? The total number of peaks in a high resolution NMR spectrum corresponds to the number of different types of the number of non-identical hydrogen atoms or protons. The chemical shifts of a specific proton specify the chemical environment or the specific type of that proton or hydrogen 1 atom. The relative peak area gives us the number of protons or the number of hydrogen atoms in a specific environment. And then the splitting pattern, okay, it follows this n+1 rule, where n is the number of hydrogen atoms on the neighboring carbon atom. So the splitting pattern gives us information about the number of hydrogen atoms on a neighboring carbon atom. Okay, it gives us information about the number of hydrogen atoms on a neighboring carbon. Now, when we talk about splitting, it only applies, okay, it only applies to hydrogen atoms, okay, or protons bonded to carbon atoms, okay. And we're also not going to be looking at the splitting patterns for carbon-carbon double bonds, okay. So we're not going to be looking at splitting patterns of protons on carbon-carbon double bonds, okay, and we're not going to be looking at the splitting patterns for arenes. All right, so we're going to be looking at splitting patterns for protons or hydrogen atoms that are bonded to carbon atoms, okay. So that could be an alkane, an alcohol, right, where the hydrogen is bonded to the carbon, okay. But we're not going to be looking at the splitting for hydrogen atoms that are bonded to alkene carbons or hydrogen atoms that are bonded to arene carbons, okay. We're not going to be, they do have their own splitting patterns, but we're going to be ignoring the splitting pattern for those types of protons or hydrogen atoms. Now, when we talk about the splitting pattern, right, again, the splitting pattern follows an n+1 rule, okay, where n is the number of hydrogen atoms on the neighboring carbon atom, okay, and only applies to hydrogen atoms or protons bonded to carbon atoms, and we're not going to be looking at hydrogen atoms that are bonded to alkene carbons or arene carbons, okay. Now, if n is equal to 0, okay, in other words, the number of hydrogen atoms on the neighboring carbon atom is equal to 0, right, there's no splitting of the peak. So that type of peak is referred to as a singlet, okay. If there's one hydrogen on the neighboring carbon, that type of peak is referred to as a doublet, because the n is 1, so n+1 will be 2, so the peak will split into 2, we call that a doublet. If n is equal to 2, again, two hydrogen atoms on the neighboring carbon, the splitting pattern is a triplet. If n is equal to 3 hydrogens on the neighboring carbon, or 3 protons, the splitting pattern will follow a 3+1 pattern, which is referred to as a quartet, okay. And then when n is greater than 3, okay, so when n is 4, we get a pentet. When n is 5, we get a sextet, and so on, okay. But anytime we have more than 3 hydrogen atoms, okay, on neighboring carbon atoms combined, we're going to call that a multiplet, okay. So singlet, doublet, triplet, quartet, and then any splitting beyond that, okay, we're not going to assign it a name, we're just going to call it a multiplet. So these are some common splitting patterns, okay, that we should be aware of, and this is what they look like, right. So here's a table that shows you the different splitting patterns, okay. Here's a table that shows you the different splitting patterns, right. Here we can see that if the neighboring carbon or equivalent protons on the adjacent carbon atom, adjacent just means neighboring carbon, there's 0 protons, we get a singlet, okay. If the neighboring carbon has 1 proton, we get a doublet, right. So a single peak will look like a double peak. It's just one peak that's split into 2. If the neighboring carbon is bonded to 2 protons, the peak is split into 2+1, that's 3, that's referred to as a triplet. Again, there's a single peak that's split into 3, okay. And notice that when this peak is split into 3, the middle part of this peak is twice as tall as the ones on either end, okay. So the triplet has a 1:2:1 ratio. So we're not going to talk about where this ratio comes from, okay. And then if there's 3 neighboring hydrogen atoms or 3 protons on the neighboring carbon atom, then the peak is split into 3+1, that is 4. That is referred to as a quartet, okay. So we can note down the ratio of the heights, right, for these splits for individual peaks, okay. So a singlet is just a peak that's not split at all. Doublet, peak is split into 2 equal parts. Triplet, peak is split into a 1:2:1 ratio, so split into 3. with the middle split being the tallest. And then if we have a quartet, okay, we get a 1:3:1 split. So we did look at a few examples, right? We looked at the example of 1,1,2 trichloroethane, right? Here we had two different types of protons, right? HA and HB. HA was a proton that was bonded to a carbon with two chlorine atoms, right? HA was bonded to a carbon with two chlorine atoms. So we expect it to shift in the range beyond 4, right? Because 3.2 to 4.0 parts per million is a shift for a hydrogen that's bonded to a carbon with one chlorine. Here we have two chlorine, so we expect it to be greater than 4 because more electronegative atoms means a greater value for the shift, or that the shift is further downfield, right? And then HB was the second type of proton bonded to a carbon with just one chlorine. We expect that shift to be in the range 3.2 to 4.0. The hydrogen is bonded to a carbon, and that carbon is directly bonded to a chlorine. So HB shifted in the range 3.2 to 4.0 parts per million, and then HA, because there were more electronegative atoms, had a greater value for the chemical shift, or it shifted further downfield, right? The relative area corresponds to the number of different protons. So the area for HA was 1, the relative area, because we just have one proton in this environment, and the relative area for HB was 2, because we have two protons in this environment. And then the splitting pattern, we looked at the neighboring protons, right? HA, neighboring carbon, the neighboring carbon has two protons, so it's split into 2 plus 1, again n plus 1 splitting pattern. So if n is 2, again the number of neighboring, if you look at HA, number of neighboring carbons, that's n is equal to 2, so splitting is n plus 1, which is 3, 2 plus 1, right? So we see that HA, the peak for HA is at greater than 4 parts per million, and HA splits into a triplet. And then HB, neighboring carbon has one proton, so n is 1, so n plus 1 is 2, so the splitting pattern is going to be a doublet. So HB splits into a doublet. Okay, so this is our high resolution NMR spectrum. The next example that we looked at was of chloroethane. Okay, now with chloroethane, this was the high resolution NMR spectrum that we got. Again, HA is just an alkane proton, right? That's the first type of proton. The three protons that are bonded to this carbon, they're all identical because they're bonded to the same carbon. That's HA, right? That's just an alkane proton. So we expected that to shift in the range 0.9 to 1.7 parts per million. And the relative area is 3 because you have 3 protons. And then the other type of proton that we had here was HB, right? That was the CH2 protons. And then the CH2 protons, right? That's HB, is a proton that's bonded to a carbon that's bonded to a chlorine. So again, a carbon is bonded to an electronegative atom, so it shifts in the range 3.2 to 4.0 parts per million, right? Hydrogen is bonded to a carbon that's bonded to a chlorine, 3.2 to 4.0. The relative area is 2 because we have 2 protons in that environment. And the splitting pattern is a quartet because the neighboring carbon has 3 protons. So that's n is equal to 3, so it splits into n plus 1, that is 4. So that's going to be a quartet. So HA splits into a triplet because the neighboring carbon has 2, so n is 2, splitting pattern is 2 plus 1, that is 3, that's a triplet. So we see a triplet at 0.9 to 1.7 parts per million for HA. And then HB, neighboring carbon has 3, so it splits into 4. So HB is a quartet in the range 3.2 to 4.0 parts per million. The relative area for the peak for HA is 3, and the relative area of the peak for HB is 2. Here are some other common splitting patterns that we should be aware of. Okay, some common splitting patterns that we should be aware of. Right, if you see two triplets, it's very common that there's two different or non-identical CH2 groups next to each other. So let's say HA is a CH2 group. It'll be split into a triplet by the neighboring 2. So HA is split into 3, 2 plus 1, 3 by the neighboring 2. There are 2 protons on the neighboring carbon. So if you look at HA, neighboring carbon has 2 protons. So this is split into 2 plus 1, that's 3. And then HB, if you look at the neighboring carbon, there's 2 protons. So HB is also split into 2 plus 1, which is 3. Okay. CH3, CH2, another very common splitting pattern that you're going to see in any compound that has a CH3, CH2 group, you're going to see a triplet quartet. Okay, very common. Triplet quartet is a very common splitting pattern that we observe. right? The reason why is if you look at the CH2, that's HA here in this case, the neighboring carbon has 3, so HA is split into 3 plus 1, that's 4, so HA is a quartet. And then HB, the CH3 here, the neighboring carbon has 2 protons, so it's split into 2 plus 1, that is 3, so HB is split into a triplet. Okay, so that splitting pattern was very evident in the previous example, right? In the previous example, we had a CH3 CH2, so we saw the triplet quartet. Right, wherever we have a CH3 CH2 group, we will see a triplet quartet. The CH3 is split into a triplet. The CH3 protons HA is split into a triplet by the neighboring 2, and then the CH2, the 2 protons here, are split into a quartet by the neighboring 3. So therefore we see a triplet quartet pattern. Okay. Another common pattern that we're going to see is 2 doublets. Okay, this could be because we have 2 CHs next to each other, so HA is split into a doublet by the neighboring 1 proton, that's HB, and then HB is also split into a doublet because of the neighboring 1 proton, right? So we see a doublet for both. It doesn't always have to be that we see 2 doublets because of this, but it could be because of this. This is just a common set of groups, or a common group that we find. Okay, we find 2 CHs next to each other, we will see a doublet. Okay, and then lastly we have a doublet triplet, another common splitting pattern when we see a CH CH2. So the CH proton, the HA, is split into a triplet by the neighboring 2, so HA is split into a triplet by the neighboring 2, and then HB is split into a doublet by the neighboring 1 proton. The next example that we're going to look at is the example of ethanol. Okay, now if you look at ethanol, we have CH3, CH2, OH, right? This is ethanol. Now I've shown the displayed formula here, right? The first question that I have is how many different peaks would we observe in the NMR spectrum of ethanol? Now in ethanol, right, these 3 hydrogen atoms are identical because they're all bonded to the same carbon. So the CH3 protons are identical, so that's one type of proton. The other type of proton, right, are these 2 hydrogens on this carbon, the CH2 protons, so that's HB. And then the third type of proton that we have is the hydrogen atom that's bonded to the oxygen, right, that's HC. So here we're going to see 3 peaks. Okay, we're going to see 3 peaks. Now HA will shift in the range 0.9 to 1.7 parts per million, right, because it's just an alkane proton, the CH3, so it'll shift in the range 0.9 to 1.7 parts per million, right? The relative area for the peak will be 3 because there's 3 protons in this environment. Okay, and then the splitting pattern will follow the n+1 rule, right? So here, if you look at the neighboring carbon, the neighboring carbon has 2 protons. It has 2 protons. So HA will split into 2 plus 1, right? N is 2. The splitting pattern will follow an n+1 rule. So it will split into 3. Okay, so it will be a triplet. If you look at HB, it will shift in the range 3.2 to 4 parts per million. So it's a carbon bonded to an oxygen, right? So the hydrogen is on a carbon that's bonded to an oxygen, single bonded to an oxygen. So it will shift in the range 3.2 to 4 parts per million. The relative area for this proton will be 2 because we have 2 protons in this chemical environment, right? And the splitting pattern will be a quartet. The reason it's a quartet, okay, again, is the splitting pattern follows an n+1 rule where n is the number of hydrogens on the neighboring carbon. If we look at HB, the neighboring carbon has 3 protons. The neighboring carbon has 3 protons, so the split will be a 3 plus 1, which is equal to 4. So we're going to see a quartet. Okay, we're going to see a quartet. Okay, and then lastly we have HC. Right now, HC is just a hydrogen bonded to an oxygen. Right, that's an alcohol proton. Shifts in the range 0.5 to 6 parts per million. 0.5 to 6 parts per million. The relative area is just 1 because we just have 1 proton in this environment, and the splitting pattern will be a singlet. Okay, because When we talk about splitting, it only applies, okay, it only applies to hydrogens bonded to carbons. It doesn't apply to hydrogen atoms bonded to oxygens or nitrogens, for example, okay? So we're not going to have any splitting for, any hydrogen atoms that are directly bonded to an oxygen. So here's the NMR spectrum of ethanol. Here's the NMR spectrum of ethanol, right? We see that HA is split into a triplet, right, in the range 0.9 to 1.7 parts per million. The relative area is 3. So this is HA, right? HA is a triplet. Relative area is 3 in the range 0.9 to 1.7 parts per million. So here's roughly 1.2 or 1.3. HB is split into a quartet. Relative area is 2. So this is HB. It's a quartet with a relative area of 2 in the range 3.2 to 4 parts per million. So here's roughly 3.6, 3.7 parts per million. And then HC, very wide range because it's an OH proton, okay, but it's a singlet. So the proton that's left over is HC. So again, what you observe here is because you have a CH3CH2, you do observe this characteristic triplet quartet splitting pattern. Because whenever you see a triplet quartet, we should be able to identify that we have a CH3CH2 present, because the CH3 protons are split into a triplet by the neighboring 2, and then the CH2 protons, that's HB, are split into a quartet by the neighboring 3. The next example that we're going to look at is the example of propan-2-ol. Okay, propan-2-ol. Okay, and again, I'm just going to draw the displayed formula. So here I have 3-carbon chain with an OH group, right? And then I have CH3, CHOH, and then CH3, right? This is propan-2-ol. So over here, right, we know that the 3 protons that are bonded to this carbon are identical, right? Again, any protons bonded to the same carbon are identical. So these 3 are the same, that's HA, right? And this CH3 group is identical to this CH3 group, right? These two CH3 groups are identical. We have a symmetric compound. So we can say that these 3 protons are the exact same as these 3 One way to figure that out, okay, is by looking at the structure of propan-2-ol and saying that, you know what, if I change this hydrogen to a chlorine, I get one chloro propan-2-ol, and similarly, if I change this hydrogen to a chlorine, I get the exact same result. Okay, if I change this hydrogen to a chlorine, I also get 1-chloropropan-2-ol. So changing this hydrogen or this hydrogen gives us the exact same result. Therefore, they are chemically equivalent. These 2 hydrogen atoms are chemically equivalent. So all 6 of these hydrogen atoms are chemically equivalent. Then you have the CH hydrogen, that's your second type. And then you have the OH hydrogen, that's your third type. Okay, so we have 3 different types of hydrogen atoms. So we will see 3 peaks. Okay. HA will shift in the range. HA will shift in the range 0.9 to 1.7 parts per million. It's just an alkane proton, right? It's on a carbon that is bonded to a CHOH. So that's just an alkane proton, right? So it shifts in the range 0.9 to 1.7 parts per million. And the relative area is 6. And then the splitting pattern over here will be, if you look at these 6 hydrogen atoms, the neighboring carbon just has 1 proton. You look at these 6, so HA, these 6, the neighboring carbon has 1 proton. So the splitting pattern will be 1 plus 1. Neighboring carbon has 1 proton, that's N. Splitting follows an N plus 1 rule, so 1 plus 1, which is equal to 2. So we'll see a doublet. Right, we'll see a doublet. Now, if you think about HB, right, this is HB. That's a hydrogen on a carbon that's directly bonded to an oxygen. It's a hydrogen on a carbon that's directly bonded to an oxygen. So it'll shift in the range 3.2 to 4.0 parts per million. Right, so the chemical shift will be 3.2 to 4.0 parts per million. The relative area will be 1 because we just have 1 proton in this environment, right? And the splitting pattern here, if you look at this hydrogen, you have 6 identical hydrogens on the neighboring carbon. If you look at this hydrogen, you have 3 hydrogens on this carbon and 3 hydrogens on this carbon. So you have 6 identical neighboring, hydrogens, or 6 identical protons or hydrogen atoms on the neighboring carbon atom. So the splitting pattern will be 6 plus 1, okay? That is equal to 7. Now, as I said, this is called a heptet, but we will just refer to this as a multiplet, okay? Anytime you have a splitting pattern greater than 4, we can simply refer to it as a multiplet. So we will refer to this as a multiplet. And then lastly, we have HC, right? HC is just our alcohol proton. So that will shift in the range 0.5 to 6 parts per million. Okay, 0.5 to 6.0 parts per million. The relative area will be 1 because we just have one proton. And the splitting pattern will be a singlet because again, splitting only applies to hydrogen atoms bonded to carbon atoms. So then if we take a look at the NMR spectrum, right, what we see is we see a peak for HA, 0.9 to 1.7 parts per million. The relative area is 6, and the splitting pattern is a doublet. Okay, so this is HA. HB, shift of 3.2 to 4 parts per million. So here we see it at 4 parts per million. Relative area is 1, and the splitting pattern is a multiplet. Right, so it's split into multiple peaks. So this is H, this is HB, okay, and then HC is just the remaining peak. That's the singlet over here. That's for the OH proton. So this is HC. So now let's solve the following question. Okay, here's an NMR spectrum. Okay, here's an NMR spectrum of a compound that has the molecular formula C4H8O. Okay, and we want to determine the structure of this compound. Okay, we want to determine the structure of this compound. So the first thing that we observe here is that we have a common splitting pattern of a triplet quartet. Whenever we see a triplet quartet, a CH3CH2 is present. So we have a CH3CH2. The CH3 protons are split into a triplet by the neighboring 2. So we'll call this HA. Okay, let's call this HA. So HA, that's the CH3 proton, is split into a triplet by the neighboring 2. And then the CH2 protons are split into a quartet by the neighboring 3. Let's call this HB, right? This is HB. This is split into a quartet by the neighboring 3. So whenever we see a triplet quartet, okay, we should know that we have a CH3CH2 group. Okay, this is HB. So we've already figured out two carbons, right? We have CH3CH2. So here we have 5 hydrogens and 2 carbons, right? So we have 2 carbons and 3 hydrogens and 1 oxygen left over. We have 2 carbons, 3 hydrogens and 1 oxygen left over. Now this C4H8O, which indicates that this is an unsaturated compound. If this was an alcohol, if there were only single bonds, for example, this would be C4H10O. So we definitely have a double bond over here, right? And then we also have 3 additional protons. Okay, so we can also look at the shift here. The CH3, that's HA, shifts in the range 0.9 to 1.7 parts per million. So that's just an alkane proton, whereas CH2 shifts in the range 2.2 to 3 parts per million, right? Roughly 2.4 parts per million. Shifts in the range roughly 2.4 parts per million. So this guy must be next to a C double bond O. That's the only oxygen containing group. That's the only oxygen containing group that would cause a shift of 2.2 to 3 parts per million. We need to figure out the oxygen containing group here. We know that if we have an oxygen containing group and we know that the CH2 shifts in the range 2.2 to 3 parts per million, the only oxygen containing group that could cause that is if this CH2 was bonded to a C double bond O, right? That would shift in the range 2.2 to 3 parts per million. So that would be roughly 2.4 in this case. So this CH2 is bonded to a C double bond O, right? Now we have 3 carbons, 5 hydrogens, and 1 oxygen. So all we're left with is a CH3. And that CH3 is right here, right? This guy will be a singlet. This CH3 will be a singlet because there's no hydrogens on neighboring carbons. So this is HC, right? We have 3 protons, right, on this carbon. and this carbon is next to a C double bond O, so HC would shift in the range 2.2 to 3 parts per million, so roughly 2.2 or 2.1 parts per million here. So that's HC, right? It's a hydrogen on a carbon next to a C double bond O, shifts in the range 2.2 to 3 parts per million, and it doesn't split. It's a singlet because the neighboring carbon doesn't have any hydrogen atoms. So this is HC. So here we get 3 different peaks, right? And this structure is consistent with the NMR spectrum. So the compound that we had was butanol. Now for the next example, okay, for the next question, I have a compound W. Okay, I have a compound W that has the molecular formula C4H8O2. Okay, and this is the NMR spectrum for that compound. So compound W has the molecular formula C4H8O2. And again, we want to determine the structural formula of compound W. Okay, we want to determine the structural formula of compound W. Now again, for this type of a question, the first thing we want to do is we want to identify common splitting patterns. Okay, so what we see here is we see two triplets, right? We see a triplet splitting pattern, and this is a common splitting pattern when we have two CH2s bonded to each other. Okay, when we have two CH2s bonded to each other, one CH2 will be split into a triplet by the neighboring CH2, right? So this CH2, okay, will be split into a triplet because the neighboring carbon has 2 protons. And then this CH2 will also be split into a triplet because the neighboring carbon has 2 protons. So we have a CH2, CH2. Now we look at the molecular formula of the compound. The molecular formula is C4H8O2. So when we see 8 hydrogens here, the first thing that we realize is that this is an unsaturated compound, right? Because if it was saturated, we would see C4H10. So it's an unsaturated compound. There's one pi bond here, right? Or there's one double bond. That's why we have 2 fewer hydrogens than we would in a saturated compound that contain carbon, hydrogen, and oxygen. That's the first thing. The second thing that we notice is that we have 2 oxygen atoms, right? Now, what oxygen containing groups would cause these chemical shifts? So we've identified that the 2 CH2s are responsible for these 2 peaks. The 2 CH2s are responsible for these 2 peaks. Those are your triplets, right? Now, what oxygen containing groups would cause these chemical shifts? Well, if a CH2 is next to a C double bond O, right, that's the only oxygen containing group that would cause a shift of roughly 2.7 or 2.8 parts per million. If it was next to a C double bond O, right, then the shift would be 2.2 to 3 parts per million. There's no other oxygen containing groups that would cause this particular shift. So one of the CH2s is bonded to a C double bond O. The next thing to note is that the other CH2 shifts in the range 3.8 or 3.9 parts per million. Now, the only oxygen containing group that would cause this is if that CH2 was directly bonded to an oxygen. It would shift in the range 3.2 to 4 parts per million. So this carbon must be bonded to an oxygen. Now, this oxygen, okay, it could be bonded to another carbon, right? Because we have 3 hydrogens here that are a singlet. So that would be a CH3. However, that CH3 doesn't shift in the range 3.2 to 4 parts per million. So this oxygen is not bonded to another carbon, right? That would not be your 4th carbon atom, because if the oxygen was bonded to that other carbon, if this was a CH3, right, then we would get C4H8O2. This CH3 should shift in the range 3.2 to 4 parts per million because it's directly bonded to an oxygen, but it doesn't. So this is not the structure, right? So this guy must be an OH. Since this oxygen is not bonded to another carbon, it must be an OH group, right? This hydrogen is going to be a singlet. This hydrogen is going to be a single hydrogen that produces a singlet in the range 0.5 to 6 parts per million. That is the alcohol proton. Okay, so that's your singlet in the range 0.5 to 6 parts per million. So this is at roughly 3.4. So what we've identified so far is this OH proton. I'm going to call this HA, right? This is HA. Then we have this CH2 proton. I'm going to call this HB. This is directly bonded to the oxygen, so it shifts in the range 3.2 to 4 parts per million. So that's HB. Then we have this CH2 proton that's next to a C double bond O, so it shifts in the range 2.2 to 3 parts per million. That's this CH2 right here. That is HC, right? HC and HB are both triplets, and the oxygen, the hydrogen bonded to the oxygen or the alcohol proton is a singlet. Okay, and then lastly, we have 3 protons that are a singlet, right? And we have 1 carbon remaining and we have 3 hydrogens remaining. If you look at the molecular formula, we have 3 carbons and 5 hydrogens already covered. So we just have 3 hydrogens and 1 carbon remaining, right? We already have 3 carbons and 5 hydrogens and 2 oxygens. We have 3 carbons, 5 hydrogens and 2 oxygens. So all we have left is a CH3. And that CH3 is a singlet. And the only place that that CH3 can come is over here, right? So that's a CH3 that's next to a C double bond O. So it shifts in the range 2.2 to 3 parts per million because it's a CH3 bonded to a C double bond O, right? And it's a singlet because the neighboring carbon doesn't have any protons. Okay, so this is going to be HD. Okay, this is going to be HD over here. So this compound is 4-hydroxybutanone, okay, also commonly referred to as 4-hydroxybutanone. All right, let's look at the next question. Okay, now I have this compound. Okay, this is compound X, and compound X again has the molecular formula C4H8O2. Okay, so X is a structural isomer of compound W. Okay, has the molecular formula C4H8O2, and again we want to figure out the structural formula of compound X. So again, looking at this NMR spectrum, we can see this common splitting pattern of a triplet quartet. When we see a triplet quartet, we know that a CH3, CH2 is present, right? The CH3 protons are split into a triplet by the neighboring 2. Okay, so the CH3 protons, I'm going to call that HA, okay, are split into a triplet by the neighboring 2 protons, right? And it shifts in the range 0.9 to 1.7 parts per million, roughly 1.2 over here, right? So this is your alkane proton, right? HA next to a CH2 splits into a triplet, 3 protons, 3 identical protons, that's HA. And then HB is your CH2 protons, right? So HB, you have 2 identical protons, right? That's split into a quartet because of the neighboring 3. 2 identical protons that split into a quartet because of the neighboring 3. So this is HB, right? And then we know that this compound has 2 oxygens, right? Again, it's an unsaturated compound because we have C4H8O2, right? So we don't have 10 hydrogens, we have 8, which suggests that it's unsaturated. So this CH2 must be bonded to some oxygen containing group, right? That causes a shift of roughly 2.3 or 2.4 parts per million. So that oxygen containing group again must be a C double bond O. So the CH2 must be bonded to a C double bond O, right? That's why the CH2 shifts in the range 2.2 to 3 parts per million, right? Roughly 2.3 parts per million. So this is bonded to a C double bond O. And then we just have one other proton left. We have 3 protons that are producing a singlet. Right? So we have 1 carbon left here. We have 3 hydrogens left, but we also have 1 oxygen left. So here we just have 1 carbon left, and we have 3 hydrogens left, and we have 1 oxygen left. Right? We have 1 carbon left, 3 hydrogens left because we have 5 over here. So we have 3 hydrogens left, and we have 1 oxygen. So you know that these 3 hydrogens must be a CH3 group. We know that these 3 hydrogens must be a CH3 group, right? And they shift in the range 3.2 to 4 parts per million, okay, roughly 3.7 parts per million. So the only oxygen containing group that could cause that shift is if this CH3 was directly bonded to an oxygen. So this CH3 must be directly bonded to an oxygen. So now we have 4 carbons, we have 8 hydrogens, and we have 2 oxygens. So that C double bond O is just bonded to an O, CH3. So we have an ester here. Our compound is methyl propanoate, right? And this CH3, that's your third type of proton, we're going to call that HC, right, is a singlet, It's a singlet because there is no neighboring carbon here, so there's no neighboring protons that would cause it to split, right? And it shifts in the range 3.2 to 4 parts per million because it's directly bonded to an oxygen. In this case, that's 3.7 parts per million. So let's look at the next question. Okay, here I have an NMR spectrum, okay, of a compound that has the molecular formula C4H10O. Okay, and again, I want to determine the structural formula of this compound and the identity of this compound. Now, if you look at this compound, okay, C4H10O, the first thing we notice is that we have 10 hydrogens here, so it must be a saturated compound, right? The only time we have C4H10, only time we have C4H10 in a compound with carbon, hydrogen, and oxygen is if it's a saturated compound. So there's no double bonds, there's only single bonds here, okay? Now, if you look at the first peak, starting from the right, starting from 0, if you look at the first peak, we have 6 protons. We have 6 protons that are a doublet. So you have 6 identical protons. When you have 6 identical protons, we have 2 identical CH3 groups. Okay, we have 2 identical CH3 groups. That's the only way in which we're going to have 6 identical protons. Okay, we have 2 identical CH3 groups. Okay, let's call that HA. Right, 2 identical CH3 groups, and those are alkane protons because the shift is around 1 part per million. So it's in the range 0.9 to 1.7. That's the only range that satisfies this peak. So these guys are bonded to a carbon, right? That's just an alkane carbon, right? And then this carbon must be bonded to one hydrogen. The reason why it's bonded to one hydrogen is because these six protons are split into a doublet. So these 6 protons are split into a doublet, which means that the neighboring carbon has one hydrogen. These 6 protons are split into a doublet, which means that the neighboring carbon has one hydrogen. So HA is split into a doublet because the neighboring carbon has one hydrogen. We also notice that these 2 hydrogens are split into a doublet. These 2 hydrogens are split into a doublet, right? So we must have a CH2 bonded to the CH. We figured out 3 out of the 4 carbons. We just have one more carbon to figure out, right? Now we have 2 hydrogens here that are a doublet. Now if it's a doublet, it means that these 2 hydrogens must be a CH2, and that CH2 must have been bonded to a CH. So we have a CH2 here, right? I'm going to call this HB for now, right? So this is HB, right? It's HB because it's 2 hydrogens, so that's a CH2. Okay, and it's split into a doublet. That's what the D stands for, because the neighboring carbon has one hydrogen. So it's split into a doublet because the neighboring carbon has one hydrogen. So here we have 6 and then 7, 8, 9 hydrogens and 4 carbons. We have 4 carbons and 9 hydrogens. So we figured out C4H9. So we just have one hydrogen and one oxygen left. So that's an OH group. And that OH group must be bonded to the CH2. That OH group must be bonded to the CH2. The reason why is because this CH2, these 2 protons, the HB, right, that was split into a doublet by the neighboring carbon that was bonded to one proton, and it shifts in the range 3.2 to 4 parts per million, roughly 3.4 parts per million in this case, which means that this carbon is directly bonded to an oxygen. That's the only oxygen containing group that would cause a shift of 3.4 parts per million. So this carbon must be directly bonded to an oxygen by looking at the shift as well. So by looking at the molecular formula, we can identify that this was an OH group, or by looking at the shift, we can identify that this CH2 is bonded to an OH group. Let's call that OH proton HC. HC must be a singlet, right? Because protons bonded to oxygens never exhibit a splitting pattern. And then lastly, we have HD, right? This is HD. This over here is HD, right? And that is a multiplet. That's a multiplet. It's split into 7 by these 6 identical protons. If you look at this CH, it has 6 neighboring protons on these 2 carbons. So it's split into 7, right? HD is split into 7 by these 6. So 6 plus 1 would be 7. And it's also split into a triplet by these 2. If you look at HD, it's split by these 6 identical protons into 7, and it's also split by these 2 identical neighboring protons, right, into 2 plus 1, which is 3. So it's actually split into 21. But again, this is just a multiplet. This is just a multiplet. So we don't need to worry about the actual splitting pattern. What we should know is that HD will be split into a multiplet because there's a bunch of protons on the neighboring carbon atoms. So this over here is HD. Right? That's our multiplet. So this compound is 2-methyl propan 1-ol. 2-methyl propan 1-ol.